Welcome back to Why This Universe. Before we begin our episode today, we have a very exciting announcement that this month we are celebrating the 1-year anniversary of Why This Universe. We are so grateful for all of our listeners and everyone who's supported our show so far. And so to celebrate, we're going to do 2 big, exciting things. So the first of those things is that we are starting a Patreon. So if you like our show and you want to be able to support us, this is how. For as little as $3 a month, you'll get a Why This Universe sticker sent to your door, and you'll be able to submit questions and listen to exclusive monthly Ask Me Anything episodes. So if you want to get in on that, go to patreon.com/whythisuniverse, or you can find the link on our Twitter, twitter.com/whythisuniverse. We are immensely grateful for any support through Patreon. The second thing that we're doing is having a raffle. So we're going to be raffling off 2 signed copies of Dan's latest book, At the Edge of Time, Exploring the Mysteries of Our Universe's First Seconds. Dan is not only a great speaker and physicist, but he's also a great writer. And if you're interested in the content that we talk about here on Why This Universe, particularly questions about cosmology and the very early universe, you'd love this book. So how do you enter the raffle? Well, if you join us on Patreon, that's an automatic entry. Or you can join us for free by tweeting at Why This Universe with a picture or a screenshot of you listening to one of our episodes. So yeah, thank you for celebrating our first birthday with us, and let's get into the episode. So we talk a lot about the standard model of particle physics on this show, and that's because it's a big deal. It's probably the most successful theory of science ever, making tons of accurate predictions that are just proven right again and again in experiments. But today on our show, we're going to dig into a situation where the standard model just fails, and we still have no idea why. You're listening to Why This Universe, a podcast where we break down the biggest ideas in physics. My name is Shalma, and I'm a PhD student at NYU.
And I'm Dan Hooper. I'm a theoretical astrophysicist at Fermilab and at the University of Chicago.
So to unpack this major problem with the standard model, we have to start with what the standard model tells us about these 3 forces of nature: the electromagnetic force, the strong force, and the weak force. You can forget about gravity for now.
So the forces that we experience in nature are communicated through space by particles we call bosons. So the electromagnetic force is really a bunch of photons, a kind of boson, passing back and forth through space. The strong force is a bunch of gluons, another kind of boson being passed back and forth through space. And if you want to have a self-consistent theory, in the 1960s, physicists thought these bosons ought to be exactly massless. They had to have 0 mass.
And this is an important detail because of some quantum mechanical weirdness.
So if you take the Heisenberg uncertainty principle, it tells you that for very short periods of time, you can increase the amount of energy of a system. So for example, if I wanted to create a heavy particle and use it to communicate a force, for a little bit of time, I could create that particle and pass it back and forth through space. But it's not very long, so it doesn't travel very far, so that force would have to be very short-ranged. Now, if I had a massless particle, like a photon, I can produce one with an arbitrarily small amount of energy, and therefore it can travel an arbitrarily long distance, communicating a very long-range force. So in this sense, the mass of a force-carrying boson is directly connected to the range of the force that it communicates.
So if all the force-carrying bosons are massless, like those physicists in the 60s thought, it would make all of the forces of nature very long range. In other words, they'd be able to act over very large distances.
You should be able to feel the electromagnetic force from a great distance, for example. Even if you're halfway across the universe or something, in principle, charged particles can tug on each other from great, great distances. So in the 60s, physicists thought these bosons all had to be exactly massless, but this wasn't concordant. It wasn't consistent with what we saw in the weak force, the weak nuclear force. This force, the force that's experienced in things like beta decay and the particles called neutrinos experience, this force seemed to be really short-ranged. It kind of died off after about 10 to the minus 18 meters. So this implied that whatever was communicating this force wasn't a massless boson, but was pretty heavy, something in the ballpark of 100 times more massive than a proton. And this didn't seem to fit into the picture. So to the physicists at the time, these supposedly heavy bosons that carried the weak nuclear force, that just shouldn't have been possible. Like, this should have broken their theory. It should have led to measurable physical quantities that would blow up to being infinity, even though that doesn't make any sense. This just did not seem to be a picture that could hold together.
So to solve this problem, a couple physicists had to get really creative. And you may recognize one of their names, Peter Higgs.
And what they proposed to solve this problem was a new kind of boson, the thing we now call the Higgs. And unlike the other particles in the Standard Model, the Higgs boson behaves differently. It carries with it kind of an energy field that extends across all space. And as other particles travel through that field, they interact with it in a way that makes those particles behave as if they had a mass. So imagine I'm one of the force-carrying particles for the weak nuclear force. We call these things the W and the Z boson. When these particles travel through space, which is filled by the Higgs field, even though they're kind of naturally massless, they interact with this field in a way that slows them down and makes them behave like they had a mass. People like to describe this as like a particle trying to travel through molasses. It just kind of it prevents them from moving quickly, makes them more lethargic, makes them behave like they're massive particles, even though in some deep down sense, they really aren't.
So by adding this sticky new Higgs field to our theories, we can explain how these particles have mass, something that was impossible in our theories before.
So when the Higgs boson was proposed originally, like, all of these ideas were super speculative. The W and Z bosons that communicate the weak force had never really been observed in any experiment, and the Higgs boson certainly hadn't been observed in any experiment. But over time, these experiments have been conducted, and they've confirmed this picture to way beyond any reasonable doubt. By the mid-'80s, the W and Z bosons had been discovered at particle accelerators. And then in the 1990s, their properties were measured in kind of vivid detail at a machine called the Large Electron Positron Collider, or LEP, which was at the CERN laboratory in Europe. It took longer for the Higgs to be discovered, but in 2012, that was discovered at the Large Hadron Collider, also at the CERN laboratory. Before that, there were some hints of the Higgs observed at the Tevatron Collider at Fermilab, where I work, but the definitive discovery happened at the Large Hadron Collider. And over these decades, it's not just that we've seen these particles, but we've measured their detailed properties, their masses and their interactions and everything about them. And all of these measurements conform to the predictions of the Standard Model theory, the stuff that Peter Higgs was writing down in the 60s and others. So I don't think there's really any question that this is really what's going on with the electroweak force.
Okay, so we have this Higgs boson that seems to solve all of our problems. So what's the issue here? What's this big failure of the Standard Model? Well, a new problem appears once we look closer at this Higgs field that we now have.
So we've got this Higgs boson, and in a really important way, this Higgs boson is different from any of the other particles that are in the Standard Model. Technically speaking, we would call it a scalar, which means it doesn't have any angular momentum. It's not spinning, and it's the only scalar particle in the Standard Model. And because it's a scalar particle, the way it interacts with the W and Z and all these other particles, the electron, muon, taus, quarks, gives them a mass. But it's also the case that those interactions also kind of return the favor, and they make the Higgs mass get bigger. So as those electrons are traveling through the Higgs field gives the electron a mass. but the electrons also have an impact on the Higgs mass. And it turns out if you calculate this, and you can pick up a quantum field theory textbook and see how you'd approach this sort of problem. And what you'd be led to expect is that the Higgs mass should be pushed up through these interactions all the way up to some very, very high scale. Like maybe the Planck mass, which is this like 10 to the 19 GeV, which is just gargantuan. It's like, trillions of times bigger than the masses of the particles we're used to talking about. So we measure this mass, and it's nothing like that. It's about 125 GeV. So we're talking about 10 to the 17, a factor of 10 to the 17 difference between what the theory leads us to expect and the much lower mass that we actually observe. And the hierarchy between those scales, between the Planck scale and the weak scale, is really at the crux of what we call the hierarchy problem.
It's basically physicists just being so wrong, and unimaginably wrong.
It's hard to be this wrong about something, Yeah, and you can think about it in another way too. Like if you don't like to think about masses of particles, you can think about the strengths of forces. So the Planck scale sets the strength of the force of gravity, which is the weakest force, a very, very, very feeble force. And the weak scale, this 100 GeV scale, sets the strength of the weak force. And because that scale is so much lower, it makes the weak force much stronger than gravity. But from a theoretical perspective, they shouldn't be. They should all kind of be about the same strength. So you can think about the hierarchy problem as a hierarchy in masses or in a hierarchy in the strength of the weak and gravitational forces. Either way, you're really talking about essentially the same thing.
So this summarizes the hierarchy problem. Basically, the hierarchy problem asks, why is the Higgs boson so much lighter than we expect it to be? Or if you squint your eyes and turn your head and look at the map a little differently, it's asking, why is the weak force so much stronger than the force of gravity?
Okay, so we've got this problem, this hierarchy problem, and it's motivated a lot of physicists to think about what could explain it. What's the reason? There's got to be a reason. And one possibility has to do with how particles called bosons interact with the Higgs and how particles called fermions interact with the Higgs.
So every particle we know of falls in one of these two categories, bosons or fermions, and which one they belong in depends on a weird property called spin. And these two categories of particles behave differently according to the laws of physics.
When a boson particle interacts with the Higgs, it increases the mass squared of the Higgs by a certain amount, probably something like the Planck mass. And then when a fermion interacts with the Higgs, it actually decreases the mass squared of the Higgs by, again, something like the Planck mass squared.
In other words, remember that the Higgs boson gets its mass by interacting with all the other particles. So if you were to add up all of the contributions from each particle to the Higgs mass, you'd have to add a number for each boson and subtract a number for each fermion.
So it's at least possible, not likely, but at least possible that if you take that positive number and add it to that negative number, they might almost exactly cancel in such a way that this thing that should have been the Planck mass turns out to be much smaller, maybe even as small as the measured value of 125. So this is like a logical possibility, but at least from my assessment, it just seems really, really, really unlikely. So I was trying to think of an analogy for this, and here's what I came up with. Like, let's say I measured the temperature of the Earth at a bunch of different cities in the Western Hemisphere. And I took then measurements of a bunch of different temperatures and cities in the Eastern Hemisphere. And I took all the Western Hemisphere temperatures and subtracted them from the Eastern Hemisphere temperatures. So the average temperature of the Earth is like 60 degrees. So these are going to be a bunch of numbers scattered around 60. And maybe I have 100 numbers minus 100 other numbers. And in the end, I don't know, maybe I have 10 or minus 10 or 22 or 1.7 or minus 3, something like this. But you'd be pretty surprised if I got 10 to the minus 17. right? If all those numbers just happen to add and subtract together so that the positive ones were almost exactly equal in magnitude to the negative ones, you'd either be really surprised or you'd say there's got to be an explanation. And I think that's where we're left in the case of the hierarchy problem. Sure, the bosons and fermions pull in different directions, but there's no reason they should pull in the Higgs mass with exactly the same strength, or almost exactly the same strength. So there's got to be something driving this. So this apparent coincidence between how the fermions affect the Higgs mass and the bosons and how they affect the Higgs mass is what physicists would call a situation that is fine-tuned. It's possible, but just like in my temperature analogy, you have to choose very specific values of the temperatures in the Western Hemisphere to exactly match those in the Eastern Hemisphere. It's possible, but it seems very unlikely. We call it fine-tuned. Now, you could invent a mechanism where the fine-tuning could be explained, or the apparent fine-tuning could be explained. So maybe now those cities in the Eastern Hemisphere have some sort of cooling and heating mechanism where their temperature is automatically driven to match the temperature of their Western Hemisphere counterpart. And that could maybe drive this analogy to something really, really close to zero when you did the calculation. And maybe that's going on in particle physics too.
And a seemingly simple solution emerges if we just consider this. If what we want is that all of the contributions from bosons almost exactly cancel the contributions from fermions, then it sounds like what we want is there to exist parallel sets of bosons and fermions.
An idea, particle physics theory called supersymmetry, every boson in nature has a fermion as a partner. We call it a super partner. And they have the same, couplings and interactions and all this stuff. And it turns out that if that's true, then all of the boson's contributions to the Higgs mass should be exactly equal and opposite to the fermion contributions, kind of giving us a reason for why these cancellations would be so precise and why it would seem to be so fine-tuned.
So supersymmetry's ability to solve the hierarchy problem, as well as a few others, made it an incredibly popular theory for many years. The only problem is that in all of our experiments at the Large Hadron Collider and elsewhere, we've seen no evidence of any of these superpartner particles. It doesn't rule out supersymmetry completely, but it definitely has put some strain on the theory. If you want to learn more about what's going on with supersymmetry, stick around for the next episode of Why This Universe.
Another possibility that doesn't involve supersymmetry is the idea that maybe the solution isn't really cooked into the laws of physics, but kind of is just a happenstance that arises from there being a very, 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 very large number of universes. So let's say there are a bunch of universes and they're more or less like ours, but in most of those universes, the Higgs is as heavy as the Planck scale. It's very, very heavy, much heavier than in our universe. And in some universes, there's better or more precise cancellations between the bosons and fermions. And some of those have a little bit lighter Higgs and some a lot lighter. And maybe one in a huge gargantuan number of universes happens to have one as light as ours. If that's the case, then our universe would be really different from all the others. And you might even imagine that the only universes that have life in them are those that have a really light Higgs boson. After all, if there's a really heavy Higgs boson, there won't be things like, the kind of nuclear fusion we see in stars. The early universe would have played out very differently, producing a whole bunch of different kinds of atoms and nuclei and stuff. So maybe all of those common universes are devoid of life. And there's kind of what we call an anthropic explanation for the hierarchy problem.
Basically, the fact that we are all alive to ask these questions means that, of course, the Higgs boson has to be as light as it is. Otherwise, we just wouldn't exist.
There's a bunch of dead parts of the universe that have, expected values of the Higgs mass, but there's no one there to see it. And then I'll mention a third idea, and there are a lot more than three ideas for how to solve the hierarchy problem. But, just for brevity, we'll just keep it to three. And this idea, like, I don't think it's the most likely explanation for the hierarchy problem, but it's one of my favorites, and it's kind of a new idea, just a few years old. The people who put it forth named it innaturalness, like the letter N, and then followed by the word naturalness. And it was written up by Nima Arkani Hamed at Princeton, Tim Cohen at Oregon, and some other collaborators. And their idea is that in addition to all the particles we know and love, in addition to the standard model, there are many other particles, copies of the standard model, that can also exist. So, for example, in addition to our electron, there are about 10 to the 16 other kinds of electron-like particles and 10 to the 16 kinds of photon-like particles, all of which are allowed to exist, and so on and so forth. But unlike our electron, all these copies of the electron are unable to interact with any of the particles we can observe. So there's a whole set of the standard model particles, and then there are 10 to the 16 copies of that.
So it would be like we are living among tons of overlaying universes that we just don't interact with.
But there has to be another element to it, because if there was really all of that energy in space, if there were 10 to the 16 times more energy than we can interact with in space, I mean, that would ruin everything. The space would expand differently, like gravity. We would feel the gravity of all those particles. So to make this work, the authors had to come up with a way to explain why most of the particles in those copies aren't very abundant. They're very, very rare in our universe. And the way they did it is they had an interaction which was strongest for those copies with the smallest Higgs mass. So our copy happens to be the one with the lightest Higgs. So it was produced in the most abundance in the early universe. And most of the others, where the Higgs mass is much heavier, they weren't produced much at all. So you get a consistent picture. It works out in the end. And it also explains, there are 10 to the 16 of these things. Ours is a weird one. That's why the hierarchy problem seems so weird.
And if we want to go out on a limb, maybe some of these extra copies of particles could be the dark matter?
Yeah, some of them could be dark matter. There can't be not all 10 to the 16 copies can be, because it would be way too much. But maybe the second and third copies that have the almost as light a Higgs boson as ours, maybe they provide us with things like dark matter candidates.
How feasible do you see this? This seems really out there.
I think it's a long shot. But, that's not criticism. I would have been very proud over it in this paper.
Yeah, no, it's really cool.
It's a cool idea. And I think it speaks to just also kind of the extents that particle theorists are willing to go to solve this problem. The hierarchy problem has been around for a long time, and we haven't been able to solve it, at least without supersymmetry. And it's driven people to consider some pretty wild ideas.
I mean, I guess it's not the first time we've needed wild ideas to change up the physics game.
Yeah, I mean, nobody, at least in hindsight, can look back on Einstein and say the problem was his ideas were too wild. I mean, they were wild ideas, but that was what was called for. Our universe sometimes is wilder than we might have otherwise guessed.
Thanks for listening to Why This Universe. As a reminder, our Patreon is now up on patreon.com/whythisuniverse. If you want to support us more and get access to some exclusive content and a free sticker. And remember, it also enters you in a raffle to win a signed copy of one of Dan's books. And you can also enter for free by tweeting at us with a picture of you listening to one of our episodes. Thank you so much for your support. Our show is produced and edited by me, Shalma Wegsman, co-hosted by Professor Dan Hooper of the University of Chicago and Fermilab, and all music is produced by Jake Kleinbaum. Why This Universe is brought to you by the University of Chicago Podcast Network.